Okay, let's get started. Today we cover economics applications. On Friday we have one more day of applications of the integral, and it has to do with probability. Monday coming up is our review day for test number 2, which is scheduled for Wednesday, exactly 1 week from today. Also coming up, the project which I handed out last time is due on Monday. Questions on the calendar? Project due Monday, test on Wednesday. Okay, so let's get started at the top of page 64 with our daily summary. Kevin. Seamus. Okay, so let's take a look at option 1. When Big Tree signs, he gets a $6 million check. And then each year after that, at the end of each year, he'll get $2 million a year. So altogether, 12 million total. Option 2 is to take a really small signing bonus of $1 million, but then get bigger and bigger paychecks at the end of his first 3 years, right? So that's 13 altogether. So which one is better? Great question. Let's assume that this person is not going to get injured and is going to get all of those payouts exactly on schedule. Is it clear that 2 is better? Why might 2 not be better? You can invest it now. You invest it, right? Like that $6 million, you can just throw in a bank and get some money on top of the money, right? And so it's not clear which one is better. So let's go to part A, Zach. Okay, so we need a formula here. Do you guys remember the continuous compounding interest formula? PE to the RT, right? Hurt? PE to the RT. In some classes, A is just the future, the amount. For some reason, our book uses B, so I'm going to use B today. Okay, so let's go for option 1 first. The first thing is the $6 million. So 6 is playing the role of the principal, right? E is just E, interest rate is R. What do we put? 10%, so 0.1 or 0.10. And then times time. We're going to run this out to the end of that 3rd year, so 3 years. So if we just crunch this in the calculator, that will give us the future value. $6 million will grow to some number. It's that number. Okay, but then we've also got money we're putting in 3 more times. So how about we do this in one big calculation? Plus, and now we're going to invest the first 2 million. So that 2 million is now the principal. 2e to the 0.10 times. Now at that 2 million comes in at the end of the first year. So how much time does that have to grow? It's got 2 years only, right? We don't get it in the beginning. Plus times 1, right? That's the middle 2 million, has only 1 year to grow. End of the 2nd year to end of the 3rd year. Okay, this last one we can just do easily, or we could use the formula, but what is, it's just a +2, right? Because we're stopping the experiment that last day of the 3rd year when we get that last check. So it is just a +2. If you're a fan of patterns, it's e to the 0.1 times 0, which will work out to the same +2, right? Okay, so somebody at each table crunch that on the calculator, but only one person do that, and the rest of the people write down the expression for option 2. And then let's just get some calculator people, at least one calculator person to give us a number. Anybody have that? How much? 14.21? Okay. So which one was better? Option 1. Even though it was 12 million total, you're getting that, you got half of it on the very first day. And so that had 3 years to grow. The option, which one is better, might change if I change it from 10% to 9% or 8% or something, right? So I'm not saying like, look at the numbers and you should just know instantly option 1, but this is the way we calculate which one is better. So this blue thing right here is what we'll use when we calculate the future value. So I'm just gonna make a note here that B is the future value. And P stands for principal, but you might also think of it standing for, initial value or present value. The value today, $6 million signing bonus today is worth whatever in the future. Okay, so future value and present value. No, I think it was different. Okay, let's take a look at part B, which says calculate the present value of option 1. At the end of the day, option 1 was worth 14.75 million, right? That's 3 years from now. But we could backtrack and we could figure out, okay, forget the signing bonus and getting 2 billion a year every year. What if they just gave Big Tree some check, a single check that they're not going to give him any more, but he invests all of that money today and it grows to exactly the 14.75 in exactly 3 years. Such a check exists, right? There is some magical number that I can put in the bank today so that 3 years from now, it'll be exactly this 14.75. So to figure out what that magic number is, well, that's the present value. That's what we're after. And so we will just use this blue formula again, but we're going to solve it for what letter? P, right? We want the present value. So the present value is equal to B over E to the RT, yeah? Or said another way, BE to the negative RT. And so the B is the future value, which is what number in option 1? That's the 1475. E to the negative R is still what, 1. T is 3 years. This was 14.75, 3 years from today is worth this amount of money today. Somebody with a calculator help us out on this one. Okay. So again, if they hand you a check today for 10.93 million, you bring it right to the bank, let it sit for 3 years untouched, and what will it be? 14.75. I have discipline. I don't know about you. All right. We understand the future value, present value, the difference here? Mm-hmm. Mm-hmm. Okay, so the first row are the two formulas that we just used right here, the B equals PE to the RT, and then solve it for solve it for P in the other equation. We're not really going to use the bottom ones, but I've included them just so that they're here. If it's not continuous compounding, but annual compounding, do you guys remember this formula? P times 1 plus R to the T. So P and B still stand for present value and future value. This is just not continuous compounding. Okay, but now we'll start doing some calculus. So let's go to Elia for 3. All right, so P of T dollars per year. So let's look at an example. Cameron, number 4. Okay, so let's do these. I don't think we need a calculator for any of this. So P of 1, we just plug 1 in for the T. What do we get? 400 times 2 squared, 1,600. Let's get some units up here. 1,600 what? Dollars per year. At the end of the first year, money will be coming in at a rate of $1,600 per year. Let's find P of 2. It's not that we just made 1,600. It's that money is coming in at that rate. But at P of 2, how much is this one? That's $3,600 per year. 48,400. Okay. So it's not to say that any of these numbers are exactly how much money came in over the course of a year. This is just that at these particular moments in time, this is the rate at which money was coming in. And so you can imagine our calculus tutoring business has a bank account, and the money in the bank account just continually rises by small little amounts, right? Like fractions of pennies, like all throughout the day and night, holidays. It's just always increasing a little bit, like the national debt clock. Maybe you guys have seen the deficit clock, right? It just keeps going up and up and up. And so it's the same idea here. It's just not going up at a linear rate. It's not going up at a constant rate. It's changing. Right. So we could maybe find how much money yeah, I think that's exactly how we would find how much money comes in a year, is you could find the area under the curve for the first year. That would tell me how much money came in. This is just one moment in time, 1,600 per year, just for that moment. All right, number 5, Alex. Let's pause right there. So Alex's question is, okay, you got this $1,600 per year coming in, but it's just coming in dribs and drabs all the time, and you want to invest that money, and you want to know how much that money grows to. But this is quite complicated, right? Because the penny that comes in this second has a different amount of time to grow as the penny that comes in this second, right? Like if we just close our calculus tutoring business at the end of a year, then the pennies that come in at different times have different lengths of time for them to gain interest, right? Like Big Tree McGee's different salaries had different amounts of time that they were going to grow. And this money is coming in continuously all the time. So it's kind of like mind-boggling. Well, how do we even keep track of how long each of these pennies has to grow, because they're just all coming in all the time? Keep going, Alex. Okay, so here's our picture. We're going to say that M is the number of years of our income stream. So like 5 years, we'll keep the calculus tutoring business open. And so what we're going to do is we're going to take this massive like 5-year interval or M-year interval. We're going to cut it into a bunch of little pieces. And the idea is that if we're on a small enough piece, then the amount of money coming in isn't going to change by very much. So for example, we changed from 1,600 to 3,600. That's a pretty significant change. But if instead of plugging in 2, we had plugged in 1.0001, then the answer is going to be pretty darn close to what number? 1,600, right? It's not going to change by much if you don't let the time change by much. So that's what we'll do. We got this little tiny red time interval. It is just blown up so we can see it. And the income streaming in on that little tiny time interval is basically constant. Doesn't change by much. And how long does that money have to gain interest? If M is the number of years, so T is the amount of time that's passed already. So how much time is left over for that particular money to gain interest? M minus T. Everybody okay with that? Okay. What's that? Yes, the answer is there, but don't look there. So let's answer this question right here. It says the future value of that money coming in on that tiny time interval. Future value. Okay, so we'll use our, again, B equals P e to the RT. Which letter is the future value? It's the B, so we're not going to change this equation. It's looking good. Okay, P is the amount of money that we are talking about investing. It's like the $3,600 per year that we had up there. It's just that little amount of time that's come in, except we don't have it for a whole year, right? It's not fair for me to say $1,600 per year. It's really only $1,600 per year coming in for like 10 seconds. So do you guys buy that if I multiply it, 1,600 per year, let's suppose it just stays 1,600 per year constantly, right? If you have 1,600 per year coming in for 2 years, how much do you have? 3,200, right? So you just take your 1,600 per year and you multiplied it by the 2 years. So that's all we're doing. It's P of T per year times delta T years. Delta T is a really small thing. It's not 2 years, it's, seconds, but it's the same idea. So I'll highlight that the principal or present value is this whole thing here. It's not just the one, it's both of them multiplied together. Times E raised to the R is just R. T is supposed to be how long the money is going to grow for. How long is the money going to grow for in our diagram? It's M minus T. So that's why this guy needs to change. So that is the expression for the present value of the money that comes in during that little tiny time interval. And then we've got lots of other little tiny time intervals up here. And so to find the present value of the whole stream, what are we going to do with all these? Sorry, I said present value. So find the future value of the whole stream. What are we doing with all of these little future values? We're just going to add them all up. And then we're going to make the time intervals smaller, equivalently more and more time intervals, and it becomes, and in the limit, what does it become? An integral. Right? Okay, so it's written down here. This is the calculation that we just did. P of T, that's part of what's highlighted in yellow. The delta T becomes the dt. E to the R M minus T is right up there. And then integrating from 0 to M, do we buy it? That's just all of your slices live between 0 and M. Same idea for the present value. We didn't do it, but it's got that e to the minus RT because that's in the present value version of that formula. Okay, so you are going to use these two formulas in just a moment, and then you'll essentially build one of those formulas on the project. So the only thing that I'll say on the activity, which begins on the next page, is that I've written here on the board, for number 1, after you've written your integral down, you can use the calculator, but I want you to do 2 and 3, those integrals by hand, okay? It doesn't say that in the instructions. So calculator on the first one once you've got the integral, but do 2 and 3 by hand. Okay, go for it.